Hey, welcome back. Today we're going to be doing a video here learning about accuracy and precision of measurement. Okay, some things we need to know. Measurements always have a value. That would be like 4.7. They always have units, centimeters, all right? They always have some type of uncertainty. At the end, we're not exactly certain if it's 4.71, is it 4.69, but there is always some type of uncertainty. A measurement is usually our best estimate. Okay, sources of error. We could have random error, means a scale, reading scale where actual value is between marks and value is estimated. Can be determined by repeated measurements. Or we could have systematic error, errors that consistently cause measurement values to be too large or too small. Reading from the end of a meter stick instead of reading from the 0 mark. That's very common. Okay, uncertainty in measurements. Another more definitive method to indicate uncertainty is to use the plus minus notation. So x would be our measured value, and then the plus minus would be our uncertainty. Example 3.84 plus or minus 0.05 centimeters. What this tells us is that our true value is somewhere between 3.79 and 3.89 because they added 0.05 to get this one, and then they subtracted 0.05 to get this value over here. All right. This means that we are certain the true measurement lies between, that should be 3.79, I don't know why they have that, and 3.89 centimeters. It's somewhere between those two. Uncertainty in measurement. In some cases, the uncertainty from a digital or analog instrument is greater than indicated by the scale or reading display. Resolution of the instrument is better than the accuracy. Example, speedometers. Example of this is as I'm driving around the lake, my speedometer on my truck quite often is reading 25 miles per hour. And on my lake, they have several solar-powered things that tell you how fast you're going, and quite often it will tell me I'm only going 21, maybe 22 miles per hour. So something's off. It's either my gauge is off, all right, or their gauge is off. But there's uncertainty in this measurement, and that's what they're talking about here with these speedometers. Okay, again, accuracy and precision. Right? Accuracy is how closeness, the certainty of a measurement of the quantity to the actual or accepted value. For example, several people might measure this cube. All right, say we have this cube, and several people, let's say the actual volume is 1.2 centimeters cubed. Well, several people measure it, and one person gets 1.21, another person gets 1.19, another person measure it gets 1.22, someone else measures it and gets 1.17. Well, all of these people are what we would call accurate. Why? Because they are close. All right. Let's say I take this to another class and I have this group of students measuring it. And these same different group of students come up with these measurements: 1.41, 1.40, 1.41, 1.41. Well, they're not very accurate, but they're pretty precise. Why? Because they keep repeating pretty much the same measurement over and over and over again. All right. So there's the difference. This group of students are very precise with their measurement. This group of students are very close with their measurement. So there can be a difference between that. We want to strive for accuracy and precision. Okay, take a look at this here. We got two students. Each measures the length of a credit card 4 times. Student A measures with a plastic ruler. Student B measures with a precision measuring instrument called a micrometer. So you can see over here, student B, they're able to get many more decimal places just by looking at this, and then looking at the plastic ruler. You can only go 1 decimal place on a plastic ruler, so they're right here. So we're plotting their data. All right, we're plotting their data. All right, and if you plot their data to the nearest tenth, All right, what we'd find out is that student A has measurements of 85, 85.1, all the way to 85.2. Student B, all of these are going to round to 85.3. Now we can only go as accurate as the least accurate. Our accuracy on our scales and graphs can only be as accurate as the least accurate measuring device. So the least accurate one is the ones that only go to one decimal place. So our scale can only go to one decimal place. That means all of these, even though someone was much more precise with their measurement, they went many more decimal places, our scale can only go to one decimal place. So we have all of these are going to become 85.3. So all four of these are right here, 85.3. So as we look at this, students A's data ranges is from 85 to 85.2. Student B's data ranges from 85.298 to 85.301. The accepted length of the credit card is 85.105. Well, who is more accurate? Student A. All right, student A is a whole lot more close. These values here are a whole lot more closer. All right, even this one is closer than 85.3. So these right here, A is closer. Student B, though, is much more precise because they keep getting the same. All right, they keep repeating the same measurement. I bet if we had them keep measuring, they would be somewhere on that same line over and over and over again. All right, if we wanted to find a thing called quantifying accuracy, how accurate are they? Well, we can find their error. All right, that's what we're talking about here, is their error. The way we find their error is we can take the mean. Mean means the average of their measured values. So student A, if you add all these up and divide by 3, you've got an average of 85.1. We subtract it from the accepted value. Again, the accepted value is 85.105. When we do that, we find out that student A, on average, is off by 0.005. So they're very close. To do student B's error, we take the mean or the average of their measured value. So we take these, add them up, divide by 4, and we get this is the average minus the accepted value. And we find out that they're off by 0.1948. So they're not as close, which means they're not as accurate. They're not as close, so they're not as accurate. Now, don't let this plus and negative stuff bother you. It just simply means how close are they. Being off by negative 0.005 in the terms of error has absolutely no difference than being off by positive 0.005. Or being off by positive 0.1948 is absolutely no different than being off by negative 0.1948. You're still off. You're still wrong. You're still not on the accepted value. How can we tell if someone's more precise? Well, what precise comes down to, they give us a really long definition here. Think about finding the range, all right? Student A has a range here. Lost my pen. Of 85.2 minus 85.0 or 0.2. Not negative, but 0.2. 85.3, if you take their greatest value minus their smallest value, if you take their greatest value, 85.701, and their smallest one of 85.698 and subtract the two, you're not going to get nearly as much. Okay, I want to change this here. It's 301 and 298. That's their greatest and their smallest values. So as you look at these two here, as I subtracted these, you'll see here right away that you've got 0.2 and 0.03. Well, which one has the smallest variation, all right? The smallest range. And that is the one that is the most precise. And that obviously then is B. All right, this one here is much more precise because we've got a much smaller number. Now, when it comes to finding this, this is a very inaccurate way of doing it, but it gives you a real quick idea, all right? the way what we typically do with precision is we look at the standard deviation. And if you calculate the standard deviation for person B, we get 0.0015, and for A, we get 0.08. Well, this is much smaller, so they have a much smaller standard deviation, which means they're a lot more precise. Okay, so let's look at something here now. I want to talk to you about something called a confidence level. If you're asked to write something with a confidence level, all right, with 68% confidence, that means we're going to do within one standard deviation of both ways. So what you'll have to do is you're going to have to calculate the mean, and you're going to have to calculate the standard deviation. So what you're going to do then is you're going to take the mean and add one standard deviation. That's going to be one of your numbers. That's how we got this number right here. Then you're going to have to take the mean and minus one standard deviation. That's how they got this number over here. And when you do that, then this becomes your confidence level. So they took the mean of 85.1 and added one standard deviation. They took the mean of 85.1 and subtracted, all right, and I can see how this can be a little bit confusing because up here they've got 0.08, down here they've got 0.07. I think it's supposed to be 0.08 in both cases, right? But that's how they got their confidence level. This is a confidence level of 68%. Why? Because when you go within one standard deviation of both directions, you are 68% confident that your value is going to fit in there. Because if you go back to our empirical rule we had with the bell chart, we said if this is our mean, all right, that was our mean, we said, that was the mu, one standard deviation of both sides, that, all right, that was 68%. 68% of the time, our answer was going to fall in that. So we're only able to say with 68% confidence. Now, if you do that exact same thing now, except go two standard deviations, so we take the mean plus two standard deviations, and then take the mean minus two standard deviations, and again, that's how they got that answer. That's how they got that answer. This is an 8 down here. All right. Then this right here is 95% confidence, because if this is our mean and there's one standard deviation and then we go another standard deviation and now we get to include all of this data, we can say that we are 95% confident that whatever value we get is going to fall within that area. Well, hey, I hope this is beneficial. I'll catch you on the flip side.